This is, again, a truly probabilistic concept, just like independence. So we're going to discuss this matter on probability spaces, okay? We're not going to deal with general measure spaces. So the idea is that if there is a random experiment that is performed and the outcome is not told, our estimate for the value of a random variable would be what? Would be its expected value, right? So in general, we can use the expected value as an average, as a rough guess of what the outcome will be if we know nothing about the outcome of the experiment, right? But if we're given some partial information, if we know something about random experiment, not the exact outcome, but maybe we know that some event occurs, then we can update our estimate for the value of a random variable using conditional expectations, okay? So these are estimates of random variables, numerical random variables, under some information. So we're going to start by discussing conditional expectations. So that's a bit unusual if you compare this to undergraduate courses on probability, where everything starts with probability A given B as probability A intersection B divided by probability of B, and then you define conditional probabilities for random vectors, random variables, like conditional distributions in terms of that definition, and then you can calculate conditional expectations just like we calculate expectations using integrals, right? So we're going to follow a different path, and there's a good mathematical reason for that. But before discussing that kind of a mathematical reason, I'd like to motivate the subject, okay? So let's say we have a probability space. So suppose the random experiment is performed. And omega is the observed outcome. So let's say we have, let us consider a positive random variable x, okay, on this space. So the realized value of x is x of omega, right? Okay. So now, suppose we are not told the outcome of the. So somebody performed the experiment, but they did not tell us. So we have no idea. But we're asked to estimate the value of x. So in this case, our estimate is simply the expected value, which is 1 over probability of this set, full set, which is 1 times the expected value of x, right? I just wrote it this way to motivate the next idea, okay? So next, suppose we're not told the outcome, but told that some event with strictly positive probability occurs. So this means what? What does this tell us about the outcome of the experiment? If we're told that A occurs, what can you say about omega? What is the meaning of A occurs if omega is the outcome of the experiment? Omega is in A, right? So we don't know omega, but we know omega is in A. So now we are in this picture. So this is A, and this is A complement. So we know omega is somewhere here. We don't know where, but somewhere in this set. In this case, we provide a better estimate for X. Okay? So this would be too rough now because we don't have to consider the case where omega is in A complement. So this is excluded from our world, and somehow we would like to live in the smaller world and take some expectation over this world. Okay? So this means to restrict X on this set, namely just assigning 0 values here, right? And taking the expected value of this. Okay? But if you do that, there is a little problem. The problem is that in the new world, the total mass is not 1. It is just probability of A. So the total probability is probability of A here. So to normalize and make it comparable to this estimate, we divide this value by the probability of A, which is the total mass assigned to A. Since A is our new world, we divide this estimate by this number, and this is going to be our updated estimate for X. We call it the expectation, conditional expectation of X under A. So if you'd like to convince yourself that this is a good enough estimate, so as a checkpoint, suppose X of omega is, let's say, X is equal to little x on the set A. In other words, it's a constant here, okay? Then conditional expectation of X given A would be what? So we know that under this set, X takes the value little x, so that I can take it out of the expectation, and this is going to become probability of A divided by probability of A. This is X, as desired, because it's a constant random variable on this set. It takes a constant value, so of course the estimate should be the value itself, because if we know that event A occurs, and there is only one candidate, right? Capital X can only take the value little x over this set. If this is the case, then this value should also be the estimate, because there is no other candidate as a value. So this should be the conditional expectation under this set A. Okay, so this is just as a checkpoint. Okay, it's just a special case. Let's look at an example to calculate a few conditional expectations given sets. Okay, let's say we're in this space 0, 1, sigma algebra being the Borel, and the probability measure being Lebesgue, which is the uniform measure, right? It's a probability measure because we are on the interval 0, 1. And let's say we have a random variable x which takes 3 possible values. So it takes the value 2 if omega is between 0 and 0.2, 1 if it's between 0.2 and 0.7, and 3 if it's between 0.7 and 1. For instance, if we're given that A, which is 0 to 0.6 occurs, so let's draw a picture. So 1, 2, 3, 1 here, and 3 here. Right? This is omega. This is x of omega. So the probability space is very concrete, not an abstract space. So we can draw a picture for the random variable as a function. Okay. So we know that event A occurs, meaning that we know that omega is between 0 and 0.6. So this is our set A. So in this case, our estimate for x is going to be this, right? So what is the probability of this set A? What is the probability of this set? 0.6, yeah. So, okay, x times indicator A. So what is x times indicator A? Well, x times indicator A is 2 on the set 0 to 0.2. It is 1 on the set 0.6 to 0.2 to 0.6. And it is 0 afterwards, right? From here on, it is 0. 1 minus 0.6. So this is 0.4, and this is 0.4. 0.8 over 0.6 gives us 4 over 3 is our estimate. If we're given that B 0 to 0.2 occurs, then the expected conditional expectation under B would be what? So this is 0 to 0.2, on which x can only take the value 2, so this should just be 2. This is a special case of this calculation, right? X takes a constant value on the set A, x takes a constant value 2 on the set B. Okay? So if we're given nothing, if we're given no information, then the estimate is this, and this is simply just the expected value of x, because this is just a full set, so it is always 1, and this is always 1, so we get just expected value. Okay. Another example. Now it's going to be an abstract example. So let's say we have some events are events partitioning omega. With positive probabilities, okay, with probability AI greater than 0 for 1, 2, 3. Okay. And let's define the sigma algebra generated by A1, A2, A3, okay? So we have a world which is divided into 3 pieces, A1, A2, A3. Okay, and we consider the subsigma algebra generated by A1, A2, A3. Okay, so now can you tell exactly what this sigma algebra is? How many elements are there in the sigma algebra? So who wants to say the elements? Yeah?
Either take the set or not, so there are 2 possibilities for each set.
Okay.
So there are 2 to 3.
Okay. So can you tell one set here?
The empty set.
Empty set, okay.
And then we can take each of them, A1, A2, A3.
Yeah.
Then we can take A1 union A2.
Which is the complement of A3, right?
That's also
So we have these sets. We can look at them separately, or we can combine them, A1 union A2, A1 union A3, A2 union A3, and omega. So we have 1, 2, 3, 4, 5, 6, 7, 8 sets. Right? This is our earlier knowledge on sigma algebras. Okay. Very good. So for each of those sets, we can calculate our estimate, right? So suppose we have positive F measurable. So F is the big sigma algebra, not G. G is a subsigma algebra of that. So F measurable random variable to estimate. So we have the individual estimates. Conditional expectation x given AI, which is defined as before, right? So in other words, on this set, this is our estimate. On this set, this is our estimate. And on this set, this is our estimate. Right? Estimates. How can you combine the 3? So this is our estimate on this set. This is on this set, and this is on this set. They are disjoint sets partitioning omega. Can you come up with a way to combine those 3 values as in the form of a random variable? Can you combine them in the form of a random variable? Can you create a random variable out of these 3 values? What kind of a random variable? Discrete? Simple function, right? You can come up with a simple function. And it is indeed the canonical representation. If you multiply those values, so take this as little a1, little a2, little a3, and use them as the values of a simple positive function on this set, on this space. So define conditional expectation of x given sigma algebra G as x given a1 on the set a1, x given a2 on the set A2 and x given A3 on set A3, right? So let us consider some properties of this new random variable x given g. Okay. So this is a simple positive function, right? And this is measurable with respect to which sigma algebra? For instance, is this measurable with respect to G? Is this measurable with respect to G? Constant times indicator A1, constant times indicator A2, constant times indicator A3. Is this a G measurable function? Why? A1, A2, A3 are in G. So their indicators are G measurable functions. And you take a linear combination of them, again, G measurable, right? So is G measurable since A1, A2, A3 are in G. Let me also say, we call it the conditional expectation of x given G. Okay, so now conditional expectation given a sigma algebra is a random variable, okay? And it has, in this example, it has those concrete values. It's a simple positive function. Okay. So let's look at the expected value of the conditional expectation under each of the sets AI. Okay, let's look at this quantity. So what does that say? We look at the conditional expectation on AI. So it is A1, A2, or A3. Well, if it's AI, this means its value is expected x given AI, right? So on this set, it takes the value x given AI. So now it's a constant. This is a random variable, this is a constant, right? If this is a constant, I can take it out of the expectation and get this, because this is a constant, whereas this is a random variable. Okay, so now what is this? This is probability of AI. And what is probability of AI times expected value x indicator AI? X given AI. So probability of AI times conditional expectation x given AI. This is going to give us expected value x under AI. So we have the expected value of the conditional expectation under set AI. It is the same as the expected value of x itself under AI. So if we multiply x by a G measurable set, the indicator of a G measurable set, or let's say one of AIs, the conditional expectation acts like a substitute for X, although they are not the same thing. It's a G measurable substitute, right? X is F measurable. Now X given G is a G measurable substitute. Indeed, this is much deeper than this. You can replace this indicator AI by the indicator of any of the sets here. And even you can replace it by any G measurable random variable V. Okay? So this can be extended from indicator AI to some positive G measurable function, a random variable V. Okay, let's do it. So let's take a G measurable positive random variable V. So let V be G measurable and positive. What does it mean to be G measurable for V? What is the meaning of G measurability? What is the meaning of G measurability? In this example, okay, where G is just generated by 3 pieces. If you have a random variable that is G measurable, what can you say about that? What can you say about the behavior of V over those regions? It's a simple partition-generated sigma algebra. It's not an abstract sigma algebra. So all that is happening here is that we have the sets A1, A2, A3, and we look at omega just like this is one single element, this is another single element, and this is another single element. Although there might be infinitely many points in each set. Right? So what is the meaning of G measurability?
Can we say all the values that we takes can be realized in A1, A2, or A3?
Exactly. So you mean that it will take just one value on A1?
Yes.
Yes, right? Do you agree? Yes, exactly. So this is indeed the meaning of measurability with respect to G. So since G is only generated by A1, A2, A3, we have V equals A1 indicator A1, A2 indicator A2, A3 indicator A3 for some A1, A2, A3. So prove it yourself if this is not clear. Okay? So now, what are we going to have? We're going to look at this expression, right? X given G times V. Okay? Well, X given G is also a G measurable thing, and it takes those values on A1, A2, A3. So there are only 3 possibilities, right? I can look at those things in A1 with the value little a1 on the set A1. I can look at these things on A2 where the values are this. So we have still indicator A2. And I can have those values on A3. So here V is A1, x given g is x given a1, and so on. So now these are all constants. So let's take them out. Okay, we took them out like we did there. So now what is this times this? Well, it is expected value of x under a1, not given a1, indicator a1, right? a2, a2, a3, a3. Okay, so let's combine everything using linearity. So a1 indicator a1, a2 indicator a2, a3 indicator a3, which is exactly what v is. So this is, again, x times v. So take any g measurable random variable v. Yeah? Take any g measurable random variable v, multiply it by x, and try to calculate its expectation. This is the same as calculating the expectation of v times the conditional expectation of x given g. So x given g acts like a g measurable substitute for x in this operation. Not in all operations, but in this operation. In this operation, in this calculation, let's say. Any questions so far? So we haven't defined the actual conditional expectation given a sigma algebra rate yet. So this is going to be for an arbitrary sub-sigma algebra G. Right now, we're just working on this specific example where G is partition generated. But this is very useful example for many ideas. So this is a very important property of conditional expectations. So first of all, we can look at the special case where v is just a constant. In other words, indicator of omega. Okay? So if you do that, what do you get? Expectation of the conditional expectation is equal to expectation of x, right? So this is sometimes called tower property. And we're going to look at a more general version in the second hour. But this is called tower property. So, okay. So you have an f measurable random variable x. And you have some partial information. And this is the case where you have no information, okay? No information. So what you can do is to estimate x given the information here, given the information stored in G. Your estimate will be x given G, right? So now this is a G measurable random variable, still random. So you can give it as input to somebody who knows nothing and ask this person to estimate. In other words, you can use it as input for a person here. So that's going to be so the estimate of this person is going to be the expectation, because no information, of the conditional expectation, because that's the input. The other path is to just give this as input to a person with no information without any intermediate steps. And this is going to be just expected value of x. This result says they are equal. Okay? So in the second R, we're going to have a similar picture where there might be some information here, and still the same thing is going to be true. Okay? We will replace this no info with less info. Okay? Another way of looking at this, so we're not going to look at the special case, we're just going to look at the general case. So let's call it the projection property interpretation, or projection interpretation, let's say. Okay, so what is that? So let's rewrite this property, okay, for every V0 that is G measurable, we have expected value of x minus, I'm going to write it as an equation, so something equal to 0 form. So this is equal to 0, okay? I'm just rewriting this expression, okay? X minus conditional expectation times V gives 0 in expectation. So this is one random variable. This is another random variable. And we may consider this expectation of a product like an inner product. Okay? So when you have, let's say, x transpose y, two vectors in Rn, x transpose y equals 0, what does that mean? What do you say in that case? X transpose y equals 0. X and y are orthogonal. We're going to say the same thing here. So treat this as an inner product. Namely, the inner product of x minus this and v is defined as the expectation of their product. We're really taking a product, but since things are random, we're taking expected value of them. Indeed, so if everything has finite variance here, etc., this is indeed an inner product. Inner product on the space of random variables with finite variance. Okay? Anyway, so what is going on here is that we have a space of G measurable random variables, and since every G measurable function is also F measurable, we can see the big word as F measurable functions. F measurable random variables. Okay, let's say this is an origin, okay? And we have this random variable x. So it's not on this plane, not necessarily on this plane, because x is just F measurable. What we're trying to do is to find the closest point in this plane to x. And this is indeed the conditional expectation of x given g. So if this is conditional expectation of x given g, we also have the remaining part. So the sum of these two should give us x, right? Just see them as vectors. This is what is left. Since this is G measurable, you can just take V equals expected value x given G here and get the orthogonality of this and that. like a right angle. Take some other v on this plane, okay? Let's say v tilde. We still have this. Because the inner product of this with any g measurable thing, so remember this is g measurable. So the inner product of this with any g measurable thing is orthogonal to this whole plane. Okay? Of course, this is just an interpretation. Things are not finite dimensional here. These are just random variables on infinite probability spaces in general, but just as an interpretation. So this is, we call this conditional expectation is the projection of x on the space of g measurable random variables. Okay? And this geometric idea is also quite in line with our interpretation as estimates, because if you look at, for instance, x given g, conditional expectation x given g, what are we doing there? So we're given the information stored in g, and we are asked to estimate x. What we do is to find the closest possible random variable in the space of g measurable random variables to x. X is f measurable. Estimating x with this information means to find the point in the space that is closest to x. And closest means it should be a projection of x onto this plane. Okay? So this is the projection. This is the orthogonal complement. Let me use a different color. So this is the projection. And this is the orthogonal complement. It just complements the projection because when you add this to this, you get x itself, right? Just x given g plus x minus x given g. And the two are orthogonal to each other, not independent, orthogonal. Right? Because this is g measurable, so I can use it as my v in this equation. So to really, to be able to call it an actual inner product, you need to work on the space of random variables with finite variance, because inner product is a function which is real valued. So you cannot let it take plus infinity or anything. And you also make sure this is not infinity minus infinity type of thing. So you have to be careful. So everything here is in quotation in some sense. But you can make it more precise if you make things square integrable, okay? Meaning that you can look at random variables with finite variance. And also here with finite variance. If you assume this finite variance condition, then things are well defined. This is indeed an inner product, etc., etc. Okay. Any questions so far? Okay. So I think we're ready to give a definition of conditional expectation. So we're going to say some random variable is called the conditional expectation of x given g if it satisfies the g measurability condition and the projection property. This is called projection property. But the question is, does it exist? Does such a random variable exist? The answer is yes. So we're not going to write it as a definition, but more like a theorem, okay? Which states the existence of conditional expectations, okay? So definition and existence. Okay. So let omega fp be a probability space. Let G be a subsigma algebra of F. Of F. So here's the theorem, which also includes some definition. So let X, let me call it 1, okay? Let X be a positive F measurable random variable. Since we deal with multiple sigma algebras, we have to say which sigma algebra we are talking about when we say measurability, measurable random variable. Then there exists a random variable x bar, a positive random variable x bar, such that it satisfies two conditions. One is measurability. So x bar is G measurable. The other one is projection property. So you can use x bar as a substitute of x if you do this operation for every positive G measurable V, G measurable random variable V. Okay? So this is equivalently, you can just work with indicators. X bar given, X bar under A is X under A for all A in G. Because these are indicators, you can just take linear combinations to pass to simple positive functions, and by monotone convergence theorem, you can pass to their limits, and this will be true for all G measurable positive random variables. And if you have this property, just specialize into indicators, and you get this property. So the two are equivalent, and you can check any of the two. Moreover, so this says existence of such an x bar. Such x bar is unique up to almost sure equality. In other words, if there is another x bar, let's say x bar bar, satisfying these two properties, then x bar equals x bar bar almost surely with probability 1. Okay? We call x bar, I'm going to say a version of, in parentheses, the conditional expectation because of this uniqueness thing, almost sure uniqueness. A version of the conditional expectation of x given G, denoted x given G. So this x bar is x given G. And parts 2 and 3 will be for the general case where x can take also negative values. Okay? But let's do it in the second hour. Okay, let's give a break now.